Today we're going to continue talking about cross products. One thing you can find with cross products is something called torque. And torque is essentially the force applied to a lever causing rotation along the axis of rotation. And so the way we find torque is we take that vector that is our rotation multiplied by the vector of force, and we end up getting something called Newton meters as our torque. And that's how it's measured. So if we look at example 4, it says Robert uses a lug wrench to tighten a lug nut. The wrench he uses is 50 centimeters or 0.5 meters long. Remember, we want Newton meters, so that's important. Find the magnitude and direction of the torque about the lug nut if he applies a force of 25 newtons straight down to the end of the handle where it's 40 degrees below the positive x-axis as shown. So essentially, they're saying this right here is the x-axis, and the 25 down is going to be in the z-axis. Okay, so this is the x-axis, this is the z-axis. Notice, is there anything done on the y-axis? There is not, which means our torque is actually going to come from the y-axis. So if I think of this as a triangle right here, okay, if this is a triangle, notice I said there's nothing with y. So what I can do is I said, okay, if we're looking for our vector, it was always the magnitude of r times the cosine of my theta, and then magnitude of r sine of my theta when x and y. Notice we have x and z, so I can actually just sneak kind of a 0 in there for the y. So what I do then is I just simply plug in the numbers that I know. Well, my magnitude is 0.5, cosine of 40 degrees. That's on the x-axis. We had 0 in the y-axis, and then we had 0.5 sine of 40 degrees in the z-axis. So I put that into my calculator, and I find that my vector ends up being 0.380, and then negative 0.32. That's my first vector, okay? So that's my rotation vector, okay? That's r. Now the next thing we needed to find was F, right? The force. Well, they tell us that the force is 25 newtons, right? That's the number we haven't used yet. So we're going to say, okay, there's nothing on the x-axis, notice it's all on the z, nothing on the y-axis, and negative 25 in the z-axis. And so to find our torque, then we have to find the cross product between r and f. So we think back to cross product. We made our matrix with I, j, k. And so we had 0.380 and negative 0.32. Then we had 0, 0, negative 25. Okay? So now we have to find the cross product of each one. So we had 0, negative 0.32, 0, negative 25, and that's the I, minus 0.38, negative 0.32, 0, negative 25, that's my j, and then I had to add k, which was 0.380, and then 0, 0, that's my k. So what I did now is, remember, I found the determinants of each one. Okay, so 0 times negative 25 is 0, minus 0 times anything is 0, so we get 0 minus 0i, so it's just going to be 0i, minus 0.38 times negative 25 is going to be negative 9.5, and then 0 right there, so that's negative 9.5 j, and then 0 times 0.35 minus 0 times 0 is just 0. Okay, so something interesting is you'll find that my vector in the end has a 0 x component a positive 9.5 y component and a 0 z component. So now they're asking us to actually find the magnitude as well. So remember how we find magnitude is we found, okay, so this is, let's say this is for our torque, okay? And so that was the square root of 0 squared plus 9.5 squared plus 0 squared. And when I did that, it obviously comes up with a 9.5 Newton meters for our torque. Then the next thing is direction. Well, the nice thing is that our direction ends up actually being parallel to the y-axis. So you can just leave it as 0 degrees on the y-axis. Here's an example that you could try on your own if you'd like. Now, something interesting about cross products. They have tons of applications in geometry. One of them actually is interesting, and it says that if you have two vectors and you find their cross product, the cross product's magnitude is actually equal to the area of the parallelogram created by those two vectors. So what we're going to do is we're actually just going to find the, if it wants us to find the area of this parallelogram, we're going to find the cross product of those two and then find that's magnitude, and it'll end up being the area of our parallelogram. So I need to make my matrix ijk, and the first one is 2, 4, negative 3, and then v is going to be 1, negative 5, 3. Okay, so I would get 4, negative 3, negative 5, 3 for my I, minus 2, negative 3, 1, 3 for my j, and then 2, 4, 1, negative 5 for my k. And so now I have to find the determinants of each one. So it's going to be 4 times 3 minus negative 3 times negative 5. All of that is going to be for I. Then minus 2 times 3 minus 1 times negative 3. All of that is for j. And then k is going to be 2 times negative 5 minus 1 times 4 for k. Alright, and so I go through all the math with it. 4 times 3 is 12 minus a negative 15, so that's going to be negative 3i. Then 2 times 3 is 6 minus a negative 3, so that would be 6 plus 3 is 9j, so minus 9j. And then 2 times negative 5 is negative 10, minus 4 would be negative 14. Okay, so I end up getting a vector that's negative 3, negative 9, negative 14. And we said if you find the magnitude of this vector, it'll give us the area of our parallelogram. So how do we find magnitude? Well, we did an example of it earlier. Remember, to find the magnitude of u cross v, the square root of negative 3 squared plus negative 9 squared plus negative 14 squared. And when I do that, I get the square root of 286, which is approximately 16.9. So, interesting enough, you take the two vectors, you find their cross product, then the magnitude of that cross product is the area found in this parallelogram right here. There's a guided practice problem I kind of drew underneath it, but you can try that problem now. So now we actually have a special object, polyhedron, that's created when you have three vectors lying in different planes. It's called a parallelepiped. And a parallelepiped is a polyhedron with faces that are all parallelograms. And the absolute value of that is called a triple scalar product. So, and it represents the volume of your parallelepiped. So what we can do is, before, in the last example, we found the magnitude of our cross product to find the area of a parallelogram. A parallelepiped, its volume can be found by finding the absolute value of your vectors. So essentially, it's like this. We multiply our vector t by the cross product of u and v. And so it ends up looking something like that. So it says to find the volume of a parallelepiped with adjacent sides t, 4i minus 2j minus 2k, u is 2i plus 4j minus 3k, and v is I minus 5j plus 3k. So we have to begin by creating our matrix. Okay, now this time we don't start with ijk, we start with our first vector, 4, negative 2, negative 2, and then we have 2, 4, negative 3, and then we have 1, negative 5, and 3. And so what we're going to do is essentially the same thing we did before, but instead of starting with I, we multiply everything by 4. So I take my matrix, which is 4, negative 3, negative 5, 3, times 4, minus 2, negative 3, 1, 3, and multiply it by negative 2. And then we add 2, 4, 1, negative 5 times negative 2. Okay? And so just like we did before, we find the determinants, which is going to be 4 times 3 minus negative 3 times negative 5, all of that, times 4, minus 2 times 3 minus 1 times negative 3. All of that times negative 2. And then we add 2 times negative 5 minus 1 times 4. Multiply that by negative 2. Okay? So 4 times 3 is 12 minus 15, so that's going to be negative 3 times 4 minus 2 times 3 is 6 minus a negative 3, which is 9 times negative 2. And we add 2 times negative 5 is negative 10 minus 4 is negative 14 times negative 2. Alright? So negative 3 times 4 is negative 12 minus 9 times negative 2 is negative 18 plus negative 14 times negative 2 is a positive 28. And so negative 12 plus 18 is 6 plus 28 is 34. So what's the volume of that whole parallelepiped? It's going to be 34 cubic units. There's another example of a guided practice problem you can sure try on your own.